Dear students, after studying this module, you shall be able to understand the consideration of various NMR instruments, know about the components of a NMR instrument, NMR spectrometer and modern NMR instruments. Know about the sample handling, locking, shimming and temperature regulation. Understand the basic data acquisition parameter in an NMR machine. Now let us introduce this module which deals with instrumentation of NMR and sample handling. Continuous wave and Fourier transform are two general type of instrumentations in NMR spectrometers. Initially, experiments were carried out with the help of continuous wave instruments. However, in 1970, the first Fourier transform instruments were built. Since then, NMR spectrometers dominate the market. Initially, NMR spectrometers were expensive and less of private companies owned them. Nowadays, modern spectrometers contain a large, strong and expensive liquid helium cooled superconducting magnet so that resolution of the spectrometer can directly depend on its magnetic field strength. Less expensive instruments which use permanent magnets hence show lower resolutions are also available. These can still give acceptable performance for many applications such as in reaction monitoring and quick checking of samples. Now, unlike in other types of spectroscopy, NMR requires high attention while preparing a sample because the quality of the sample has a profound effect on the performance of the corresponding spectrum. Therefore, simple but necessary steps should be followed to prepare an NMR test sample. Now let us begin with the details of instrumentation of NMR spectroscopy. There are two types of general instruments for NMR, namely continuous wave, that is CW in short, and pulsed or Fourier transform, FT in short. Early experiments were conducted with continuous wave instruments, and in 1970 the first Fourier transform, that is FT instrument, became available. In the present time, CW NMR, that is the continuous wave spectrometer NMR, have almost been replaced with pulsed FT NMR instruments. However, due to their low maintenance and operating cost, they are still commonly used for routine proton NMR spectroscopy at 60 MHz. Low resolution CW instruments require only water cooled electromagnets instead of the liquid helium cooled superconducting magnets found in higher field FT NMR spectrometers. These two spectrometer designs can be described in the following way. Students, first we will consider the continuous wave or field sweep instruments in detail and their instrumentation. These systems are currently obsolete except for a few wide line experiments that are performed in special solid state NMR applications. A schematic representation of a 60 MHz continuous wave NMR spectrometer is shown in this figure. This figure shows you a schematic representation of a typical continuous wave NMR spectrometer. Now, the sample is held in a strong magnetic field and the frequency of a source is slowly scanned. There are two orthogonal coils of wire that serve as antennas for radio frequency radiation. This can be seen easily in the figure. One coil is attached to an RF generator and serves as a transmitter. The other coil is the RF pickup coil and is attached to the detection device. Since the two coils are orthogonal, the pickup coil cannot directly receive radiation from the generator coil. One coil supplies a constant RF frequency and the second coil detects the RF emission from the excited nuclei as they get relaxed. When a nucleus absorbs RF radiation, the reorientation of the nucleus spins takes place. The excited nucleus, when comes to the ground state, re-emits the RF radiation in a direction that can be received by the pickup coil, and the instrument responds by recording it as a signal or a peak. This detail is shown clearly in the figure. In some instruments, rather than changing the RF frequency, the magnet field is varied and RF frequency is kept constant. As the magnetic field strength increases, the precessional frequency of all protons also increases. When the precessional frequency of a given type of proton reaches the value of 60 megahertz, it is said to be in resonance. The two coils can be adjusted to vary the applied magnetic field slightly by passing a current through them, causing each chemically different proton to come into resonance sequentially, which can be recorded in the form of signals or peaks. Now students, varying the magnetic field is exactly equivalent to varying the RF frequency, and a change of 1 ppm value in the magnetic field strength has the same effect as a 1 ppm change, that is decrease, in the RF frequency. Hence, changing the field strength instead of the RF frequency is only a matter of instrumental design. Instruments which vary the magnetic field in a continuous manner, scanning from the downfield end to the upfield end of the spectrum, are known as continuous wave instrument. I hope now you can better appreciate the meaning of continuous wave instruments. The peaks generated by a continuous wave instruments have a ringing, a decreasing series of oscillations that occurs after the instrument has scanned through the peak. Ringing occurs because the excited nuclei do not have time to relax back to their equilibrium state before the instrument scans the proton. The excited nuclei have a relaxation rate that is slower than the rate of the scan. As a result, they are still emitting an oscillating, rapidly decaying signal which is recorded as ringing. Fourier transform instruments or FT NMR instruments. These are the second in line of the type of instruments in NMR spectroscopy. To record a complete spectrum using a continuous wave NMR instrument, it requires a long time, that is a few minutes, because each transition is induced in succession by continuous scans from low field to high field. Therefore, each different type of proton is excited individually and its resonance peak is observed and recorded independently of all the others. In FT NMR instruments, an alternate approach is used where all protons are excited simultaneously. Thus, in Fourier transform NMR, the sample is irradiated at a fixed field strength with a strong pulse of radio frequency energy containing all the frequencies over the proton range. All protons are excited simultaneously and then begin to return, that is to decay, to their original spin states and re-emit RF radiation at their respective resonance frequencies, creating an interference pattern in the resulting RF emission versus time known as free induction decay or FID. The frequencies are then extracted from the FID by a mathematical technique called a Fourier transform. An FT-NMR spectrometer consists of a control console magnet and a coil of wire that serves as the antenna for transmitting and receiving the RF radiation. Only one coil is necessary here because signal reception does not begin until after the end of excitation pulse. Because the FID results from the emission due to nuclei in all environments, each pulse contains an interference pattern from which the complete spectrum can be obtained. Since each FID acquired in 1 to 2 seconds, it is possible to acquire hundreds of FIDs in just a few minutes. And the FIDs can be summed and averaged to greatly improve the signal to noise ratio of the resulting FID. Now, all these details that I have just mentioned are easily seen in this figure that you can see, which shows a schematic representation of a modern FT-NMR instrument. Now students, after having studied about the instruments and their details, let us now come to the sample handling in NMR. To obtain high quality NMR spectra, it is important to prepare the sample correctly. There are some facts which we should follow to make the sample appropriate in order to record appropriate spectra. Let us now consider the first fact to get a good spectra. First is the NMR tube selection. For recording NMR, we should use high quality NMR tube. The diameter of the sample tube should be the same to the coil diameter of the NMR probe in the magnet. We should not use a 5 mm NMR tube in a 10 mm probe unless we have no choice remaining with us. Bad quality NMR tubes contain regions where the tube wall thickness varies, and this variation makes our sample difficult to shim well. Let us now come to the second fact. Second is the sample purity. The sample must be as pure as possible. Peaks due to impurities can make the spectrum unnecessarily complicated and difficult to comprehend. One should ensure that the sample is free of magnetic impurities, as these can distort the magnetic field and hence degrade the spectrometer resolution. Third, we consider the solvent selection. Samples must be prepared using high quality deuterated solvents. We must try to use individual ampules rather than taking solvent out of a bottle that originally contained 50 or 100 grams of the solvent. Deuterated chloroform more than 6 months old may be acidic enough to exchange with labile protons from our sample. Therefore, we must take care if our compound contains labile hydrogen atoms or hydrogens particularly susceptible to acid catalyzed degradation. If the solvent itself has protons, the spectrum will be saturated with signals from the solvent itself, rendering it unreadable. As a result, solvents without protons must be used. Although there are several solvents that lack protons, such as carbon tetrachloride, these solvents do not dissolve all the compounds. Thus, in practice, deuterated solvents are generally used. The nuclei of deuterium also exhibits nuclear spin. and therefore also resonates, but they absorb RF radiation over a very different range of frequencies than protons. In an NMR spectrometer, a very narrow range of frequencies is used, covering just the frequencies absorbed by the protons. For example, a 300 MHz spectrometer will use a pulse that consists of frequencies between 300 MHz and just 5000 Hz over it. The frequencies required for deuterium resonance do not fall in this range. So, the deuterium atoms are invisible to the NMR spectrometer. All these solvents are routinely used for NMR experiments, and many other deuterated solvents are also available commercially, although they are quite expensive to use. For example, you can see the deuterated chloroform, the deuterated methylene chloride, the deuterated acetonitrile, the deuterated benzene, and the deuterated water. Next, the factor to be considered is the sample concentration. Ideally, students, 1 to 10 milligram of the sample, except in the case of polymers, is generally required to obtain a proton NMR spectrum of an organic compound. Although it is possible to obtain spectra from smaller quantities of compound, that is in dilute concentrations, much greater care needs to be taken with sample preparation so that peaks from common contaminants such as water and grease do not overwhelm peaks from the sample, and also it may take hours to acquire it. If the sample is too concentrated, then broad signals are observed because of increased viscosity of the solution, which shows molecular tumbling. Slow molecular tumbling only partially averages the dipolar and chemical shift tensors, depriving us of the full orientational averaging that occurs with rapid molecular tumbling. Only complete orientational averaging allows us to observe narrow resonances. To get 13C NMR or the carbon NMR or depth NMR spectrum, more amount of sample is required, that is almost 10 to 50 milligrams, with a longer period of time for acquisition, that is 10 to 30 minutes, due to reduced sensitivity of carbon 13 relative to the proton. Next in this factor is solubility. Sample should be completely soluble in the chosen solvent. We must avoid having solids present in the tube. The better is the solubility, better is the sensitivity of the experiment conducted. Solid particles distort the magnetic field homogeneity, which causes broad lines and indistinct spectra that cannot be corrected. Water must also be removed by drying the sample prior to dissolution. It is good in practice to filter the NMR solution before putting it in the NMR tube. Adding small amount of extra solvent to the solution may help minimize the line broadening caused by the microscopic nucleation of colloidal or crystalline particles present in saturated solutions. The solvent produces NMR signals which will obscure regions of interest in the spectrum. Let us take an example. Benzene, that is deuterated benzene, C6D6 and toluene is not suitable for the compound having several aromatic rings. Third in this factor would be temperature. The melting and boiling points of the solvent should also be considered, especially when the NMR has to be taken above the room temperature. For example, DMSO is not appropriate solvents for measurements below 16 degrees Celsius as it crystallizes at that temperature. Fourth in this factor would be residual water peak. Almost all NMR solvents contain traces of water and most are hygroscopic, and hence the longer they are stored, the more water they will contain. The presence of HDO peak will only serve to degrade the quality of the NMR spectra. The fifth in this factor would be the cost factor. Cost is also an important factor. In general, students, prices increase with the number of deuterated atoms in a solvent. For example, CdCl3, D2O are relatively cheap, whereas deuterated benzene and toluene, which contains 8 deuterated atoms, DMF, which contains 7 deuterated atoms, are expensive. Hence, we must first check the solubility of our compound in cheaper solvents and then look for the expensive ones. Next factor, students, is the sample volume. The samples must be prepared up to a certain height, approximately 4.5 centimeters and 5.5 centimeters of the NMR tube. Less sample height in the tube is very difficult to shim and causes considerable delay in recording the spectrum. Samples, on the other hand, having too much of solvent, that is a long height, are also difficult to shim and are a waste of the costly solvents. After preparation of the sample, we should ensure that the cap is tightly kept onto the tube to minimize the solvent loss through evaporation. In a 5 millimeter diameter tube, a volume of between 0.6 to 0.7 ml is normally optimal. Next comes the cleaning of NMR tubes, and probably this is the most important. Before using, NMR tubes should be washed properly and dried. The NMR tubes should be first washed with detergent solution and rinsed several times with distilled water and then again several times with acetone or with some other suitable solvents. We never use high boiling solvents such as DMSO for the final rinse because of difficulty in evaporating that solvent. After the complete wash, NMR tube should be kept in a cool oven, say 50 degrees Celsius, for several hours to ensure the removal of residual acetone. An alternative method is to blow nitrogen or air through the tube while warming it gently for a few minutes with a heat gun. Do not dry NMR tubes in a hot oven, that is above 100 degrees Celsius temperature, as the high temperature may result in deforming the NMR tubes. The most proper way to keep NMR tubes in an oven is by putting them flat on a paper towel or a clean cloth. We never store NMR tubes upright inside a beaker or an Erlenmeyer flask. If we lean our tubes in a beaker in a drying oven, gravity will bend the tube and make it out of uniformity. If we lay our tubes flat for too long, though, they will develop an oval cross section and thus will no longer be concentric as we want them to be. Now students, let us summarize this module. We have learnt that there are two types of spectrometers. One is the continuous wave and the one is the Fourier transform spectrometers, and we have learnt in detail about their instrumentation. FT-NMR spectrometers are used nowadays because they take less time and give better resolution of the spectrum. It is important to carefully follow the steps while preparation of an NMR sample. Less than 10 milligram of sample is taken in an NMR tube and a deuterated solvent is used to attain a height of 4.5 to 5.5 centimeters in an NMR tube. Cleaning of the NMR tubes is the most necessary step to avoid the presence of any impurities. Now students, from this module I hope you have learnt the techniques of NMR instrumentation and the precautions while preparing a sample for NMR. This will help you understand and give you a better understanding of the NMR in the future.